You've been there. You write hundreds of lines of code, hit compile, and the entire build crashes, all because you forgot a single closing bracket. But before you even run the compiler, modern IDEs like VS Code already know where the mistake is. A red squiggly line appears under the exact character where the structure breaks. This happens instantly, powered by a specific algorithm called a syntax checker. At the core of that syntax checker is a data structure called a stack. Think of a stack like this vertical drop tube. When you add items, like an open parenthesis and then an open bracket, they pile up. The new bracket rests directly on top of the old one, physically blocking it. Unlike a normal grocery line, a stack enforces a last in, first out, or LIFO rule. You cannot access the bottom item until you remove the top one. Because a stack requires items to be removed in the exact reverse order they were added, it mirrors the structure of nested code. If you open a function and then open an array, you must close the array before you can reach the end of the function. The physical top-only restriction of the stack matches that nested hierarchy. Let's see this in action on a perfectly balanced string of brackets: an open parenthesis, an open bracket, a close bracket, and a close parenthesis. The syntax checker follows two main rules. Rule 1. Whenever the algorithm reads an opening bracket, it pushes it into the stack to remember it for later. Rule 2. When the algorithm reads a closing bracket, it immediately checks the very top of the stack. It asks, does this incoming closing bracket correctly match the shape of the most recent opening bracket? If they form a valid pair, the algorithm pops the top element out of the stack. That pair is now closed, verified, and cleared from memory, exposing the next bracket underneath. If a string is perfectly balanced, the algorithm falls into a steady rhythm. It pushes open brackets down and pops them off the moment their matching partner arrives until the entire string is processed. Code in the real world is rarely perfectly balanced. We need to see what happens when we feed the algorithm a broken string that starts with a closing bracket. Think about the mechanics of the stack for a second. What mathematically happens if the algorithm reads that first closing bracket, goes to check the stack, and finds absolutely nothing inside? This is a stack underflow. If you try to read the top of an empty stack, the program crashes. To prevent this fatal error, the C++ code intercepts the check, returning an immediate false the moment it sees an unmatched closer. Then there are mismatched types. If the stack has an open parenthesis, but the incoming character is a closing square bracket, the shapes collide. The pair is invalid. The stack rejects the operation, and the syntax checker throws an error. Robust algorithms use these checks to transform potential system crashes into predictable exit points. By explicitly defining what to do during underflows and mismatches, the code maintains control over every possible state, valid or invalid. There is one final logic trap. What if the algorithm processes the string, successfully pops a pair of brackets, but runs out of characters while an opening bracket is still sitting in the stack? Reaching the end of the text file does not guarantee the code is correct. An orphaned bracket means a function or array was opened and left hanging, keeping the syntax broken. Because of this, the final step of the algorithm checks the stack itself. By returning whether the stack is completely empty, the algorithm gives its final verdict. If it's empty, the code is flawless. If anything remains, it fails. Let's look at the performance scaling. This algorithm reads each character in the string exactly once. It pushes or pops in constant time, meaning the total time to run scales linearly with the length of the string. That gives us a time complexity of O of n. The space requirement is also linear. In the absolute worst-case scenario, a massive file made entirely of opening brackets, every single character gets pushed into the stack. Memory usage scales directly with the input, resulting in a space complexity of O of n. A stack might seem restrictive because it only lets you touch the top item, but that strict last-in, first-out constraint is precisely why it operates so efficiently. By enforcing order, it transforms a simple list into a fast, highly predictable engine for evaluating nested data.